y and z direction. The prime over c is gamma e over c minus delta c. This is a transformation for energy and momentum in relativity. So from here, we actually want to derive what's actually important for us in this class, which is force transformation. Recall that. But let me move on with this first. Let's just calculate the force transformation, and we'll go back to electrostatic again or EMM again. So we want to calculate F, and F is, as we know from mechanics, is dp, right? Okay, and I want to look at forces in two different frames. O and O prime. Okay, if I know the force in O, what's the force in O prime? Okay, and to do that, we have two components here, two parts, and they all transform under Lorentz transformation. First, you have the momentum, right, and then you have also the time. Okay. So let's see here. Let's look at, this is actually a change in momentum, right? And then this is just to cut it out. This is the limit as delta t equals to 0. Of delta t equals delta t. Okay. So let's look at delta p. Delta p prime, just from the form momentum, the expression of the form momentum, you have delta px. This is just exactly the same discussion when we're talking about Lorentz interaction. Delta px prime then is equal to gamma delta px minus beta delta e over c, right? And delta e prime over c is given by gamma. And gamma here is 1 over squared over 1 minus b squared plus c squared. Okay, delta E over C minus beta px. Okay. Now, if I have a force F in the O frame, right? Take the O frame. A force F. Right? Then the change in momentum, delta Px, force in the x directions. Okay. Delta Px, then this is just Fx. Right? Okay, and then from mechanics you also know that the x, then this is equal to 1/2 the acceleration, right? And the acceleration is just Fx over m. Let's start writing m naught because in relativity this is the rest mass of the particle, right? Times delta e squared. Okay, and let's see what do I need here. I want to consider, since we want to look at the transformation of a for momentum, I need to know what delta E is, and delta P in terms of change in time. Right? The energy change is basically equal to work done. Okay? And the work done then is just the force times delta x, right? This you recall from mechanics. Okay, so this becomes then just 1/2 Fx squared. By the way, I don't get force in the x direction, that's what I'm considering right now. But by m naught times delta t squared. Okay. Okay. So if I look at that expression over there, then delta px prime just becomes, well, let's actually group things, right? If you look at this as a function of delta t then delta x is actually proportional to delta t squared, right? But here delta p is proportional to just delta p. The energy is also proportional to delta t squared. Right? Since I'm taking the derivative in the limit when delta t goes to 0, I can drop all the terms that is higher order than delta t. Right? So everything that has a delta t squared, I'm going to drop it. Right? So delta px prime, then this becomes gamma times delta px. Right? Because this part here, I'm going to drop that. Okay? Same thing with the delta t prime. Delta t prime then from Lorentz transformation, if you recall, is equal to gamma delta t minus beta delta x over c, right? Remember this from Lorentz transformation, okay? And also delta x is proportional to delta t squared. So I'm going to drop that too. Right? So I'm left with just this expression. Okay? So if I look at the limit, then delta px prime divided by delta p prime, then this is equal to gamma delta px over gamma delta t. Right? And this is just delta px over delta t, which is equal to the force in the x direction. So the transformation of the force in the x direction is just simple. It's just fx prime is equal to fx. Right? Or, since x is the direction of motion, sometimes you write it this way. F parallel is equal. Okay? But how about for forces in the perpendicular direction? Can I erase all this? Midterm is this Wednesday. Homework 8 is till Friday. It's very short. There's only 3 problems. Bring your blue book, calculator, sheet of notes. Don't worry so much about expression of all the gradient and divergences in a spherical coordinate or cylindrical coordinate. I'll write it out if you ever need it. Also, don't forget to study about dipoles. As I was telling Charlie, dipoles are more important than monopoles in a lot of things that we study, unless you're in a Large Hadron Collider, right? All chemistry, all atomic physics study dipoles. And also, since some people left early, don't forget, because I especially require you, don't forget the expression for this part of an accounting. This is the electrostatic energy goes as electric field squared integrated over the whole volume. So that's also important. Image charges, write down all the formula for image charges. Make sure you don't forget that.
What do you mean by dropping it?
Yeah.
Sorry?
When you say you drop it,
because if I take the limit, right? So, let's see. I can write it out, right? So if it, then this becomes gamma delta t minus beta, and if I look at the expression for delta x, which is then just 1/2 fx over m naught.
oh, you're saying it approaches 0 faster.
Right, delta t squared over over c, right? Okay, this is the expression for delta t prime, right? So I want to look at things linear in delta t prime, linear in delta t, and this is actually quadratic, right? So in the limit when delta t prime goes to 0, right? I mean, they approach 0 the same way, right? Delta t and delta t prime, they have to approach 0 the same way, linear. So I'm dropping things that is of higher order. Right? Same thing here with the expression for delta E. Delta E is just the work done on the particle, right? And it's proportional to also delta T squared, right? You know this from mechanics. Same thing when you're doing a derivative, right? When you try to take a derivative of x squared, right? Then you expand x squared or x to the power of n, right? and then you actually drop higher powers. Just the
So
linear powers.
When you look at
But
something
in the
linear,
limit.
when you look at something linearly versus like
Uh-huh.
quadratics, is it just you're just looking at a specific area of what, like what's the physical meaning of wanting to do that?
Oh,
I mean, mathematically, I get it.
mathematically, if I just have a function,
Is it like you're looking at a specific area, like when you take the derivative, like and
right.
okay.
Say if I have a function y is equal to x to the power of n, right? So I want to look at the final derivative of y prime, right? And this is just the limit, say delta x equals to 0 of delta 1 equals delta x,
Yeah.
right? So this becomes delta y is just x plus delta x to the power of n minus x to the power of n, right? So this becomes x plus delta x to the power of n minus x to the power of n divided by delta x, right? So when I do that, I normally just present the power of so this is x to the power of n plus n delta x plus n minus 1 over 2 factorial x to the power of 1 delta x. You guys remember? I don't remember anymore. But this goes as delta x squared. Right?
Yeah, I just
Something like that. If I pull the delta x out, is that right? Sorry.
It's okay.
X to the power of n, 1 plus, right? The whole thing divided by delta x, right? So if you take the limit when delta x goes to 0, then you're left with, well, this is minus x to the power of n, so just cancel the 1, right? So I have just the limit of delta x goes to 0 of n. Is that n minus 1 somewhere? I'm quite messing up my
Yeah,
out.
that's fine.
N minus 1 and delta x over delta x plus something that's proportional to delta x squared over delta x cubed over delta x, right? And then you just take the limit that this goes to 0, and then you can drop all that. Right? So I'm doing exactly the same thing over here. Okay? And I found that this is the case. Now let's look at the Fy in the perpendicular direction. Okay? Fy prime, then it's just it's equal to dp y prime over dp prime. Right? This is the limit of delta p prime versus 0 of delta p y prime over delta p prime, right? But this becomes much simpler because delta py is just delta py prime. That is the other part of the Lorentz transformation, right? Remember, this is the orthogonal direction. It doesn't really transform. And this just becomes delta py over gamma delta t. So it's delta, it becomes 1 over gamma delta py over delta t. Right, and the limit when this goes to 0, then this just become 1 over gamma fy. Okay. So this is how it transforms. Fy prime is equal to 1 over gamma fy. Okay. Or sometimes, because you don't really worry about whether it's y or z, then you have a perpendicular prime is 1 over gamma and so this is what we know about force transformation, right? 3-force transformation. So it's a standard classical force. So this is what you see in the lab.
Other question.
So now you have machinery. Yes.
When you go over there, like alpha delta t? Like,
Yes.
I'm kind of confused because in the first equation.
Alpha, there is no, oh, this is not alpha, this is proportional.
Oh, okay.
Proportional. Okay. Sorry about that. Is it? Yeah, proportional, not alpha. Was that the confusion? No, okay. So, let's see, where are we? So now that we know how we already know, okay, let's see. For the past week, right? Now we know how electric field transform, right? And we also know by now how forces transform, right? So you have a machinery to actually understand forces of moving charges. Okay. In particular, let's talk about an example. The thing is, on a moving charge, physics is simple. In the rest form of the particle. Right? We spent the past, however, 4 or 5 weeks talking about static configuration, right? So we know all about it. This is just chapter 1, chapter 3 of the cell, right? Maybe 4, we can do, right? That involves current. So if you want to find forces in the moving frame, all you need to do is calculate everything in the rest frame, right? And then do all the transformation in the lag frame. Okay. So this is the tricky part. The tricky part is about notation, right? So we have done this transformation between prime and prime frame, but from now on, O is going to denote lag frame. And this is just a standard with physics, you know, either in Purcell or in Jackson is also there. It's all done this way. O prime is a particle frame. Okay. So, in particular, the example I want to look into is forces between two moving protons, right? So I have two protons, one is above the other. They're moving with some velocity v. Okay. Let's call this proton 1, that's proton 2, I'll call it. And let's look at things. Of course, we're describing this in our lab frame, right? In our lab frame, this thing is moving to the right? But we don't know yet what the forces look like in the lab frame. We just have to go through it step by step. But in O prime, you know things are simple. Right? Suppose you put this whole thing in a box with I can remember who's always in the moving frame. It's Emad, right? Looking at this P1 and P2, Charlie is the one who's always in the lab frame. Okay. Then the force here, this is always a prime frame. The force F prime within these two is very simple, right? The force is just repulsive in the z direction. Let's call this the z direction. Also, I don't know why I'm using z instead of y. Then it's just 1 over 4 pi epsilon naught e squared over c squared in the z direction. Okay, c prime squared.
Is that FC or F prime?
F prime, yeah, F prime is enough, right? Or well, you know, C prime if you want. But remember, this is all the transverse direction. C prime is equal to C, right? Okay. So this is the force, right? This is from electrostatic in the rest frame, okay? Or just to backtrack a little bit, the electric field in Z direction also, let's call it E prime, is given by 1 over 4 pi epsilon naught. E, if we call E is positive over C prime squared in the C direction, right? And E is always the same whether you're in lab frame or in a moving frame. Remember that the first invariance that we learned, the first invariance of relativity is the invariance of charge. Okay? Charge doesn't transform. Q is always Q in anything. Okay? So things are very simple in a lab frame. Not in the lab frame, in the moving frame or in the rest frame of the particle. This is called the rest frame. Okay. But now let's look at the transformation. Let's look at what happened in a lab frame. According to Charlie, we're going to O. First of all, the electric field, right? So this is two protons moving in that direction, right? The electric field in C is in the Z direction. First of all, is greater. Again, you see the notation is flipped. Be careful, right? Always remember, transverse electric field is larger, is smaller in a rest frame. Right? Always remember transverse E field is smallest particle in rest frame. Okay? Recall that example that we have, right? If I have a plate, right? This is this is just E, right? In the rest frame of the parallel plate, I have E. I've boosted with some velocity V, right? Then according to Charlie, what he sees is gamma, right? He sees something larger than the rest frame. So always recall, always remember this. Then you'll never make a mistake of the notation, right? See how the notation is not consistent? But just remember that part. Just like in Lorentz contraction, always remember moving rod is shorter, right? And the same thing here with the force, right? This is how you, the mnemonic for remembering it is that transverse force is the largest in rest frame. Okay. This is how you would remember it. Gamma, by the way, gamma is always greater than 1, right? So this is the rest frame, right? In the rest frame, in the rest frame, you have a force, but according to the lab frame, in Charlie's frame, the force is less, right? The force is always largest in the rest frame of the particle. It's the other way around.
How does that work though? Because isn't force just Q times E and then Q is invariant, right?
This is the thing, this is the tricky part, right? So yeah, there is an inconsistency here, it seems, right? Transverse force is largest in the rest frame, but transverse electric field is the smallest in the rest frame. But force and electric field are two different things, right? So, I mean, we haven't done anything wrong, we just have to trust the physics that we've been doing, right? So far, nothing is wrong. I haven't connected the electric field to the force yet in the electric. All I know is that the electric field transforms this way, and the force transforms that way, right? So let's look at the force here according to Charlie. According to Charlie, then Fc should be equal to 1 over gamma Fc prime, right? So then it's equal to 1 over gamma, what is Fc prime? Did I erase Fc prime? No, Fc prime is over there, right? 1 over gamma, 1 over 4 pi epsilon naught, E squared over C prime squared. Right? This is the force. Okay? It's smaller, right? But also, I want to try to do this slowly because it's kind of confusing. But if you look at the transformation of the electric field, right, then Charlie Sauce's electric field EZ equal to gamma EZ prime, right? EZ is a larger electric field. So it's equal to gamma E over 4 pi epsilon naught E squared. Okay? And the force due to the electric field, then force due to electric field, right? This is the force due to the electric field of a moving charge, right? In the lab frame, right? Lab frame is just equal to E times Z, right? Okay, but recall that there's a gamma here. So this becomes gamma E squared over 4 pi epsilon naught C squared, right? I'm cavalier with the C and C prime because they're the same, right? This is in the transverse direction, right? So there is a discrepancy, right? The discrepancy is this force is actually larger than that force, right? Because this is multiplied by gamma. That's actually divided by gamma, right? So the electrical force is actually larger than the real force. Right? The real force, if you trust relativity, that is the real force. Right? But the electric force gives you something larger, by quite a bit. Right? And the discrepancy, delta, this is a discrepancy by the way. And it's just, I'm just taking the difference. Gamma E squared over 4 pi epsilon naught C squared minus 1 over gamma E squared over 4 pi epsilon naught C squared. Okay? And if you do all the math, did I not finish it? If you do all the math, then this becomes gamma 1 minus gamma squared, right? E squared over 4 pi epsilon naught C squared. Right? This is the difference. Okay? Let me erase this since we know what we're talking about already. You know? Let me actually just erase that one. Okay? 1 minus gamma squared is just, sorry. 1 minus 1 over gamma squared is just, what is it? What is 1 over gamma squared? 1 over gamma squared is just 1 minus beta squared, right? Okay. So 1 minus 1 over gamma squared then becomes beta squared. Okay. Beta, by the way, is B over C. Right. Then the discrepancy delta then just becomes gamma beta squared E squared over 4 pi epsilon naught C squared. Let me recreate this. This becomes beta squared gamma E squared over 4 pi epsilon naught C squared. Okay, and this is just the electric field, right? This is the electric field. This is by Charlie. Okay. Notice that the discrepancy is proportional to delta is proportional to beta squared. Right? This is very important because in most cases beta by the way is less than 1, right? And in most cases it's a lot less than 1. So this discrepancy is actually small. It only becomes very important when your speed is close to the speed of light. Okay? And that's the difference. And another thing that you have to realize that there's a difference. This is the force, right? The force is E and B in the lab frame. So is a force from the electrical force like this, right? But the real force from relativity, the real force is actually slightly smaller. This is the real force. Oh. Okay. So there is another part of the force that counteracts the electrical force, right? Okay, and this is delta, right? Because the difference between the electrical force and the total force is delta. Okay? And delta is proportional to, again, this is proportional to beta squared, right? Meaning that it's proportional to velocity squared. There is a velocity going in that direction. Velocity going in that direction, they give you force actually transversely.
Do you have to transform the distance between the two particles?
Yes, you do, right, except that this is a transverse distance. Remember from Lorentz transformation, right? Only, you have a contraction only in the x, in the y, the c is the same, right? So there is no need to do that here, right? C is always equal to c prime. Okay. So that makes it simpler. Okay? So notice that this extra force, right, is perpendicular to the velocity. Right? I guess it's by symmetry, but it's also delta going in that direction, right? Okay, on the other particle. I don't want to confuse you. It's a delta on the particle number 2 going in the y direction, and it's proportional to the velocity squared in that direction. Right? And the effect is small because it's good as beta squared. Okay? So this points to, well, there is something else beyond electrical force. Right? And that's the prelude to actually discussion on magnetostatic. We don't have to approach magnetostatic this way. You know, back to a lecture 3 lectures ago, you can introduce this experimentally with the experiment of Husted, and the whole thing was ready for it. You know, when Husted did the experiment, only a few years later, Ampere's characterized everything, and Faraday reduction happened, and you die. Right? You don't have to do it this way. But this just shows that there is, and eventually you'll see the formula, right? But this shows that there is some kind of consilience or coherence between electrical forces, magnetostatic, and also relativity. Right? This difference comes from relativity. Question like this? Is this clear so far? Is this confusing? It's kind of confusing, right? That's why I'm going through it slowly.
The 1 over gamma is like the second term, is that
Yes.
one?
Mm-hmm.
Just the 1 over gamma.
1 over